Good morning everyone. Today we are going to discuss some advanced topics in industrial robot programming. These are soft float functions, force-torque sensor integration, and the concept of a shared workspace between multiple robots. These three ideas are extremely important in modern automation because they allow robots to work more flexibly, more safely, and more efficiently. By the end of this lecture, you will not only understand what these concepts mean but also where and how they are used in real industries. Let us start with soft float. Normally, when we program a robot, we define exact positions and paths. The robot then tries to move very rigidly along these defined coordinates. But in reality, the environment is never perfect. The part might be slightly shifted, the fixture may not be aligned exactly, or the tool position may vary a little. If the robot behaves like a rigid machine, it will collide, jam, or even damage the tool or the workpiece. To solve this problem, the concept of soft float is used. Soft float allows the robot to be flexible in certain directions. You can imagine it like a spring. If the robot moves forward and it feels resistance, instead of pushing hard, it can slightly move sideways or up and down to adjust itself. This flexibility allows the robot to continue its task even when the environment is not perfectly accurate. Let me give you a simple example. Suppose a robot is trying to insert a metal pin into a hole. If the hole is exactly aligned, the task is easy. But if the hole is misaligned by even half a millimeter, the rigid robot will push against the hole and get stuck. With soft float, the robot senses the resistance, shifts slightly, and guides the pin into the hole smoothly. This is very useful in tasks like machine loading, insertion operations, or assembly processes. If you look at the diagram here, the red arrow shows the rigid path. The robot follows this strictly with no adjustment. The blue wavy line shows the soft float path. It looks flexible because the robot adapts its motion when small forces are applied. This is the essence of the soft float function. There are several benefits of using soft float. First, it reduces programming time. Without soft float, we must program the robot with extremely precise coordinates, which takes a lot of time. With soft float, we can allow small tolerances and the robot automatically adjusts. Second, it increases reliability. Since the robot can adapt to minor errors, it does not fail as often. Third, it reduces investment cost. In many industries, companies invest in high-precision fixtures just to make sure the robot can work rigidly. But with soft float, cheaper fixtures are sufficient because the robot compensates for inaccuracies. And finally, it improves productivity because the robot avoids unnecessary stops and jams. You can see applications of soft float everywhere. In automotive factories, robots use soft float when loading gear shafts into gearboxes. In plastic industries, robots unload parts from injection molding machines, and since the position of the part may vary slightly, soft float allows the robot to pick the part without damaging it. In electronics, during small assembly tasks, soft float makes it possible to align delicate components without applying too much force. Companies like ABB provide soft move, and FANUC offers compliance options, which are real industrial examples of this function. Now let us move to the second topic, force-torque sensor integration. A robot without sensors is like a blind person who cannot feel anything. It will move along its program, but it cannot sense if it has touched something or if it is applying too much force. A force-torque sensor gives the robot the sense of touch. It measures the forces and torques acting on the robot's end effector. This means the robot knows how hard it is pushing, pulling, or twisting on the part. Force torque sensors are usually mounted on the wrist of the robot, between the arm and the tool. They can measure forces in all three directions and torques around all three axes. This allows the robot to perform complex tasks like polishing, sanding, inserting parts, or even hand guiding by humans. For example, imagine polishing a curved surface. Without a force sensor, the robot may push too hard in some areas and too little in others, leading to poor surface quality. With a force torque sensor, the robot maintains constant pressure, resulting in a uniform finish. Another example is assembly. If you want to insert a peg into a hole, the robot uses the force data to align the parts automatically, even when the hole position varies. Force torque sensors are also used in safety. If the robot hits something unexpectedly, the force sensor detects this and immediately stops the robot, preventing accidents. In collaborative robots, or cobots, force torque sensors are essential because they allow safe human-robot interaction. Integrating a force torque sensor involves both hardware and software. The sensor must be mounted, connected, and calibrated. Then, in the robot programming environment, the force data is used to control motion. For example, you can write a program that says, move forward until the force in the Z direction exceeds 20 newtons, then stop. This allows very intelligent and adaptive behaviors. Now let us move to the third and final topic, shared workspace between robots. In many industries, you don't just see one robot, you see multiple robots working together. They may be assembling a car, packaging products, or welding large structures. When two or more robots share the same space, coordination becomes very important. If robots are not coordinated, they may collide with each other, cause damage, or stop production. Shared workspace programming ensures that multiple robots can safely and efficiently work side by side. One simple method is zoning. The workspace is divided into zones, and only one robot can enter a zone at a time. For example, if robot A is inside zone 1, robot B must wait until zone 1 is free. This prevents collisions. Another method is scheduling. The robots are programmed with a sequence so that one completes its task before the other starts. This is common in assembly lines. A more advanced method is real-time communication. Robots exchange data about their positions and movements. If one robot is moving into a space, the other robot automatically avoids it. This requires a central controller or direct robot-to-robot communication. For example, in automotive assembly, one robot may be holding a car body while another robot welds it. Both robots share the same space but must stay synchronized. In packaging, one robot may be loading items into a box while another seals it. Again, proper coordination is required. The benefits of shared workspace programming are clear. Productivity increases because multiple robots can work in parallel. Flexibility improves because tasks can be distributed among robots. Safety is ensured because collisions are avoided. So, to summarize, we studied 3 advanced programming concepts today. Soft float allows flexibility and compensation during motion. Force torque sensor integration gives the robot a sense of touch, enabling delicate and adaptive tasks. And shared workspace programming allows multiple robots to work together safely and efficiently. These 3 technologies are essential for modern automation. They help industries achieve higher productivity, better quality, and improved safety. In your future projects or research, whenever you see robots in action, Try to observe whether they are using soft float, force sensors, or shared workspaces. It will help you connect theory with practice. Thank you.